hot out here.
It is. Man, I wish we were biking today. We'd go biking right into that lake again.
I could have made at least 30 feet today.
I'm sure you would have gotten better.
Yeah. All right, so we're at an observatory.
We are.
No better place to talk about an 11-dimensional model.
Oh, that reminds me. I have a couple questions on 11 dimensions and how it relates to gravity.
Okay.
But first, let me make sure I understand 11 dimensions.
Okay, good.
So we have the 3 dimensions of space that we know, kind of the X, Y, and Z.
Good.
That we know of. And then...
What are they made up of?
Oh, quanta.
Yes, the whole collection of quanta makes that.
Yes, yes, a volume of quanta. Now we have the volume, which is inside the quanta.
Good.
That's another 3 dimensions.
All right.
So we're at 6. Okay, now in between these quanta, there's a volume.
Yes.
Which is the last 3 spatial dimensions.
Perfect.
Okay, so now we have 9. The last 2 are time. So time as we know it is when one quanta, what's the word?
Resonates?
Yes, when it resonates. So each time it resonates, it's 1 ping in time.
Yes, 1 tick.
1 tick
I like
in
ping,
time.
that's cute. Okay.
All right. So the last dimension of time is as the quanta moves through superspace.
Yes, so we call it super time because it's motion through superspace.
Super time.
Okay, good. So 3 independent types of volume. Each volume is 3-dimensional, so that's 9 space dimensions. 2 different time dimensions. One's a familiar time related to the pieces of space. Every time they resonate is 1 tick of time for each location. And the one super time, which relates the motion of the quanta through super space.
Okay,
Good.
great.
So that's all 11 dimensions.
Not too bad.
Yeah.
All right, so now my question on gravity. You were explaining earlier how, let's say if my right arm and my left arm were going straight through space, through the universe. Now, if there were more quanta, if it was more dense over here, and I wanted to go straight, my line would actually go this way.
Yes. So because the definition of straight means both sides are going to equal go through the same amount of space.
Right.
Right. That's how it means to go straight. If space is more dense in one region than it is in another region, then in order to continue going straight, you must go like this.
Right.
Good.
Okay, so that kind of explains, for example, why the moon orbits around the Earth.
Yes.
I mean, the moon is technically going straight through space.
Yes, it's going straight through curved space.
Straight through curved space, yes.
Good.
Okay, so now my question is, how does gravity relate to mass?
Okay, so the more mass, the more gravitational field there's going to be.
Right.
So mass originally comes from the quanta sticking together. So if you imagine a whole sea of quanta all moving around, bumping into each other, bouncing off, but there's 2 of them in the whole sea that are stuck together.
Okay.
The rest of them are individuals. Well, the motions of all the ones that hit this one are going to be different than the motions had they hit a single one.
Right.
So this conservation of momentum idea, this elastic interaction idea, is that this motion is going to be slowed down as it bounces off because this has more inertia. Yeah, more mass.
Okay.
So around the clumping, there's going to be this field of things that are moving slower, and it's all out to things that are moving faster, which is going to be less density out there and more density in here.
Right.
Now, more mass means more pieces stuck together.
Okay.
Which means you get a larger clumping in the middle, which means it's going to have a higher gradient, a bigger change from here to there of higher density to lower density. So more clumping of space, the more changes in the geometry of space is higher mass, which causes higher gravitational field.
Okay, so basically the Earth is a bunch of quanta stuck together.
Yes, well, I mean, it's got a lot of space between it too. So all the particles of mass that make up the Earth are all regions where the quanta are stuck together. But if you zoom way out from the Earth, you can pretty much simplify the whole thing and pretend that the whole thing was one mass right in the center.
Okay.
Okay.
Well, cool, that explains it.
All right, now that we understand gravity and that it's a distortion in space-time and the density of space-time, that opens up the door for us to understand 2 other big mysteries, dark matter and dark energy.
So they must have something to do with gravity.
Yes,
or
with distortions in space-time.
Okay,
Good.
Great.
All right, how about we go inside the observatory here and get out of this heat and talk about dark matter?
Sounds great.
Okay. So let's talk about dark matter and how the mystery has come together, the things we've discovered that led us to believe in dark matter to begin with. And then we're going to see how our picture automatically solves that mystery. Okay, so when we look at the orbital velocities of stars around galaxies, so you see a whole cluster of stars that form together in a galaxy.
Like the Milky Way?
Like the Milky Way, which is a spiral galaxy, okay? And then if you keep track of how all the stars are slowly moving around the center of that galaxy through time, you can infer the gravitational pull between that star and the center of the mass.
Right.
Okay? If you equate that to Newton's equations for gravity or Einstein's equations for gravity and equate their velocity versus how much mass you know is there, everything is entirely perfectly matched up until you get to the very edge. And you get to the edge of the galaxy and somehow all the stars start moving about as if there's far more gravity right there.
Huh.
Yeah, very strange. And it's just out of the edges. Okay, now this is a flat disk, relatively flat disk. And then all the edges where that flat disk go through this bubble on the outside, they all start acting weird. Okay? Somehow there's more gravity there pulling on them, so their velocity changes. And
I wonder if that has anything to do with quanta.
Yeah.
Okay,
well, it has
keep
to.
going, keep going.
Okay. So this is what needs to be explained, is why that's there. Why is there apparently this halo on the outer edges of galaxies, and not just our galaxy, several galaxies. The colder galaxies have halos that are in closer, and the hotter ones have them further out. Some of them, we don't see halos, meaning we don't see stars that are being affected by a halo, which means they might still have a halo, but it's further out of reach of all the stars. It hasn't come in yet. But this is what we're finding. And these are relatively new discoveries in science, in astronomy. So explaining why these stars are acting differently is what we need to do. We attribute that effect to some cause, and we call it dark matter.
Okay,
So,
we have no idea what it is.
no idea, yeah. We know that it has a gravitational pull. It's affecting things gravitationally. So we're going to assume it's some type of matter, yet we can't see this matter. We can't find it. No light shines off it. We can't locally identify it. We haven't been able to make particles in the lab that seem to represent it. So we just call it dark matter. So dark, it's ominous.
That
We don't
makes
know what it
sense.
is. Okay, so we need to explain what causes that effect.
Okay.
Now, in our 11-dimensional model, imagine we have a galaxy, which is a bunch of things made up of mass, which are stuck together quanta, and you zoom further out, you have clumps of quanta, and then it fades out in density around them. But if you have a whole galaxy, on average, everything around the middle of the galaxy is much higher density.
Right.
And as you get out the edge, it gets much, much lower
Less
density.
dense.
Good.
Okay.
What is the temperature doing?
Well, near the center of like the star, it would be hot.
Yes.
And then as you got further and further away, it would cool down.
Okay, so what's the background temperature of just the space? If you're not actually in a star or anything, if you're just in space inside of solar systems versus in space way far away from any solar system?
Within the solar system, I'd say it would be pretty hot.
Yeah, it's, well, relatively warmer than further away, right?
Yes,
So if you're in the
yes.
middle of a galaxy where there's lots of stars nearby, the temperature of space is going to be higher than if you're getting really far out to the edges.
Right.
Okay, why I'm bringing temperature up? I mean, what does that have to do with anything? Well, since we're envisioning the pieces of space as quanta moving around, interacting in the same way that molecules would, we have something that we can call phase changes. Okay? So a familiar material that undergoes phase changes that we know of is water, right?
Right, mhm.
What phases does it experience?
Well, there's ice, liquid, and gas.
Okay, so you can have water, so H2O molecules, arranged in such a way that we call it water. But if they change their arrangement in a very specific way, they turn into ice.
Right.
Or if they change their arrangement into another specific way, they turn into steam. But it's still just H2O molecules.
Mm-hmm.
So this different geometric arrangement of the fundamental pieces of the material defines the characteristic of the material. So since space is made up of individual pieces, the arrangements of these pieces, the change in density, are what we blame gravity on. If that change in density could just somehow change at some point, have some effect or go through a phase change, that region where it was undergoing a phase change, where the density changed from one value to another value, would end up affecting, well, it would cause a warp in space-time. So we would blame it on gravity.
Okay.
So it is a distortion, right? In the same way
Right.
that gravity is a distortion.
Right.
So in 11 dimensions, since we can see all these pieces and see changes in densities, we're actually required at some point to have the possibility of phase change of space. So
That
space
makes sense.
itself changes,
Okay.
right? And if we undergo this phase change, how would you expect the distribution of the phase change? If our heat source is all in one central galaxy, where would you expect to find phase change from that?
Basically, where it's cooler,
Yeah.
you'd find a phase change.
So it would be radially defined. So there should be a sphere around the center of a galaxy, no matter what shape the galaxy is, right? A flat sphere or a flat disk galaxy, or a cigar galaxy, no matter what, so around the center of it, there should be a sphere that goes around it, and the edges of that sphere defines the region where the phase change begins.
Okay.
And it's
where
only
cool enough for
where
the
it
phase
becomes
change.
cool enough. So that's something that's really special in this model because it actually lines up with what we find. Cigar-shaped galaxies, flat disk galaxies, no matter what the shape of the galaxy, when we find its halo of dark matter, it's always a disk. I mean, it's always a sphere around the disk or the cigar or whatever.
That makes sense.
Yeah. So here it is, space-time, a phase change, which is just a change in the geometric arrangements of the quanta of space, causes a difference. And that difference, just like in gravity's case, affects the motion of things. And this effect we call dark matter.
Okay. So essentially, during the phase change, that must mean there's more quanta there, which
Yeah,
means
relative
there's
density
more
goes up.
mass.
Yes,
Around there.
effectively more mass.
Okay.
So we're not actually causing the same type of mass that we have in stars and stuff where everything's actually stuck together. All we're doing is actually packing them closer together.
Okay.
But since it was fading out, getting less and less packed, and then went through a phase change, and all of a sudden we have denser space, that change right there manifests as a curvature in space-time, and therefore anything moving through it will appear to be affected by gravity because it's going through a different type of space.
Okay, that's cool.
All right, the only
Too
other
bad.
thing on top of that is that after you get through the region where the phase is changing, and then it's all the same phase out there, you no longer see a difference because gravity only shows up where it's a change in the geometric structure.
Okay.
So we only see it right in the halo region.
So it's out there everywhere. We
Yeah.
just can't
From
tell
then on
unless
out
there's a
until you
change.
approach another galaxy where it's warming back up. Yeah,
Well, I was going to say, too bad we can't see it.
Yes.
Or then it would be
But
so
we
much
can
of a
now in our
mystery.
heads.
That's true. I can
makes
see it in
sense
my
of
head
it.
now.
All right, great. So now we got gravity. We understand the connection between gravity in 11 dimensions to dark matter, both fundamental mysteries that make sense now. Let's go out in the telescope field here and talk about dark energy.
Okay, sounds great.
Good.
All right, so now that we've talked about gravity and dark matter and how it's a warpage of space-time, and essentially this means that there are different densities of quanta
Yes.
in the universe. What about dark energy?
All right, dark energy, just like the other two, they're all simply linked. It all comes from the same concept that we can now intuitively access in 11 dimensions. So gravity was a density distortion starting from high density close to the mass and lower density as you go out.
Right.
And dark matter, as we just discussed, was a phase change which increases the relative density as you get to the outside edges of the galaxy. So a phase change in the density of space again.
Right.
So both of these distortions, these density distortions, cause effects that we give names to and label, gravity and dark matter. Dark energy is perhaps even a little more interesting. So first we should talk about the mystery of dark energy, so we understand exactly what needs to be solved, and then we'll use our new 11-dimensional model to explain all of that in one simple picture.
Cool.
All right, so dark energy, when we look up at the stars and look at the ones at different distances, okay? So we train a telescope at them, we focus it, and we take the light that comes into our telescope and put it through basically a prism and split the light into a rainbow, including all the wavelengths beyond both ends of what our eyes can see. And we have a computer analyze the light that comes from the stars. First thing you notice is these stars give off characteristic signatures. Okay, it's like fingerprints of light. All stars use hydrogen, compress it into helium, and that process gives off a certain color, and that color has very specific wavelengths that come out. And you can use those wavelengths to match the fingerprint of the star. All right, and since all stars do that, and stars have other colors, other wavelengths, because they have other processes going on also, but they all at least have that. You can then compare that to all the other stars with the same light spectrums, and notice that they all are basically the same. Well, exactly the same. Except when you look at further and further stars, you notice that the fingerprint, the hydrogen alpha line, for example, is shifted a little bit. And the stars that are even further away, that same band is shifted even more. So we call this redshift because the color itself moves more into the red direction, okay, instead of the blue direction. So it's not the color it originally was, and we need to explain how it changed. And addressing that, we call it redshift, but what causes it, we call dark energy. Okay, so it's this redshift we have to explain, and particular details of how the redshift comes about. So if we take a map, a time map through all the stars in the galaxy all the way to the edge of the visible universe, and try to map out how this expansion has changed through time, we have 3 different phases. The first phase is entirely theoretical, so we don't actually measure it by looking at the stars out there. It's thrown into our models to help it make the Big Bang theory, which is now called the inflationary Big Bang model, match up with observation. Okay, so for the first fraction of a second, small little amount of time, the universe underwent an extraordinary, immense, really fast expansion. So it went from being way smaller than an atom to roughly this size in a very small amount of time, and that's actually a little faster than the speed of light, well, significantly faster than the speed of light. So nothing traveled through space faster than the speed of light, but the size of the universe expanded faster than the speed of light. All right, so that's the first phase of expansion. And the next phase, after that, it started tapering off. The universe was still getting bigger and bigger, but less and less rapidly.
Right.
Okay, and it kept tapering. And then, about 5 billion years ago, it started speeding back up. So we're now in a phase where the expansion of the universe is accelerating. And that's a huge mystery in just itself. Just that last phase is a big mystery. But we need something that will explain all 3 phases. Okay?
Right.
Why the universe is expanding to begin with, and why does it have 3 different phases? Okay, so that's the mystery of dark energy, explaining that. And now we want to use our 11-dimensional model to explain what's actually occurring. Okay. In order to do so, we need to understand Doppler effect or redshift. What do you know about those so far?
Basically, if there's a light and it's moving away from you, that will cause a redshift.
Oh, away from you causes redshift, yes. And if it was toward you, it would make a blue shift.
Right.
Okay.
And then it also has something to do with the Doppler effect of sound.
Yeah.
So if a sound's coming towards you, it'll sound higher, and then if it's moving away from you,
okay, those two are the exact same effect. If it's sound in air, we call it the Doppler effect. So the sound of a train, as it coming towards you, or the pitch goes down as it goes away, and the pitch is high as it coming towards you. When it's right there, right in the middle, that's the actual note that the person who's blowing the horn hears. That's the original sound. Okay, light does the same thing, but the wavelength of light changes color instead of sound, right?
Okay.
And light's traveling through space, sound's traveling through the medium of air. Right? If you remove air, there is no sound. Just like if you remove space, there is no light. Okay, so when we observe something, or let's stick to the sound version. If we take a tuning fork, and I go into a train tunnel past where you can see me, and you know I only have one tuning fork, and it's tuned to middle C, and you've checked it out beforehand and listened to it and have your little instrument to verify exactly what the note is, and I go way back into the tunnel and slam it against the wall, and you hear a B note, which is just a little flat from the C.
Right.
Well, how would you explain the fact that you heard that note?
Well, if it was coming from the C tuning fork, one thing I could assume was that you're walking away from me.
Ah, good. And this is the traditional explanation. So if I'm moving away from you at just the right speed, I'll be playing a C note, but when it gets to your ears, because I'm stretching out the note from my motion, it is heard by you as a B note. Now, I could also be holding still and you moving away from me, right? So just relative motion between the two of us.
Right.
All right, this is exactly how everybody interprets the information from the stars. We see light from the stars, it's redshifted. We automatically assume that redshift means motion.
That they're moving away from us.
Yeah, and it's a valid assumption, but it's not the only explanation. There is another way to get redshift, another way to get the Doppler effect. Okay. And it seems a little less intuitive in the sound version, but that's only because we're stuck on short timescales and short distances. If I was in that same train tunnel and I hit the note, and the instant I hit the tuning fork against the wall, and the sound started traveling toward your ear, if during the time it took to get to your ear, the atmospheric pressure significantly dropped, the note you would hear wouldn't be a C note, it would be a lower than a C note. Okay?
So let's say if the temperature dropped, wouldn't that cause a change in pressure?
Yes. So pressure, temperature, volume, all these things are related. If you change one, the other two need to compensate. So that's a really good example of how we could find a natural environment to make this actually work on Earth, right? Depth of a tunnel, like 2 miles down where it's really hot, really high pressure, you could be making a sound down there, and as the gradient changes, of the temperature gradient and the pressure gradient changes at the top of the tunnel, somebody at top would hear different sounds, different notes than the sounds being created at the bottom. Okay, that's a really good point. This means we can reinterpret all the information of the redshift of the stars, because now there's another way. Before we went from 4 dimensions to 11 dimensions, if you were to try to talk about the pressure of space, it's not defined, right? Everybody, what do you mean the pressure? What's the pressure of what?
Right.
But now we have a quanta moving around, bumping into each other, just the same way that we have here in the air, a whole bunch of molecules elastically running into each other and holding a certain average pressure over a certain range, right? Changes as you go up, but now we can apply the same idea to space. So if the pressure of space were to somehow change over time, say a million, a billion years, then what should you expect as light travels through it?
Well, it would lose energy and you'd get the redshift.
Good. It loses energy as it travels through it because the pressure is going down, and so you're going to get a redshift. You're going to see a color that's less energetic, more redshifted than the original color that was sent out. Perfect. And this is exactly what dark energy turns out to be. So the further away you get, the more time it's taken for that light to travel to your eyes.
Right.
Okay. When the more during that time range, the pressure of the universe has decreased, so the more redshifted you're going to get, which is exactly what we're trying to explain.
Right. So it's not necessarily that light is moving. It's just.
Yes, exactly. Now things can still be moving around and causing motion Doppler effect, but this change in pressure is the part that's actually causing what we're blaming on expansion.
Right. Okay.
Good. So now we can understand in general expansion. Why would it be that we had the 3 different phases of expansion? Why is it accelerated now in how fast things are cooling or how fast the pressure is decreasing? So right now the pressure of the universe must be, or pressure of space, must be decreasing faster than it was 8 billion years ago. Why would that be? Also, what's the whole inflationary part about? Any guesses?
You mean the initial inflationary period?
Yeah.
Guesses on the change in temperature?
Any of these, yeah. Well, why is the pressure decreasing to begin with?
I guess it takes energy to keep something hot.
Okay.
So.
But if these collisions between all the quanta were perfectly elastic, then all the energy would be conserved.
So quantas must be slightly, just a little inelastic.
Just a little bit inelastic. So every time they collide, they have to internally readjust all the parts they're made out of, which takes some geometric energy from the larger system. So every collision is almost elastic, but it gives a little bit of energy to the dimensions on the inside of each quanta. So that means we're losing energy over time, which means the universe should be cooling over time, which is something we have already measured. The universe is definitely cooling over time.
Right.
And since pressure and temperature are related, the pressure of the universe is decreasing over time. But now it's decreasing faster. Why would the quanta be losing energy faster now than they were 8-9 billion years ago?
Well, if you think of quantas as springs, in the beginning, they very elastic springs are extremely elastic.
Yeah.
And then let's say now that spring is about half as elastic. It's going.
So it's lost most of its energy. It's only vibrating a little bit. Okay.
Right. And so now there's actually. I guess I'll try to explain it. Okay.
That's perfect. So if you take a really, really expensive spring, one that's meant to be as elastic as you can be, we can approximate it as being 100% elastic, but it's still going to have a little bit of inelasticity in it.
Right.
And we suspend a weight from it and stretch it and let go. It's going to start going up and down and up and down and up and down. Now let's put it in a vacuum so that we don't have air friction or anything like that, air resistance. If we come back a day later, this thing will still be going up and down and up and down, but not quite as much as it was originally. Right? Now, if we make a graph to plot the range of how far up and how far down it's going with each resonation there, the graph will show over time that it decreases and decreases and decreases. But as it gets down here and it's only moving up and down so far, it's got a lot less energy in the motion of the spring.
Right.
But the friction in the spring is still constant. So compared to the energy in the spring, the friction is relatively higher now.
Right.
So it's going to be dampening it more than it was before.
So it gets more inelastic faster as
Yes,
it gets
at the
smaller.
end. Okay, so the inelasticity becomes more of a pressing, a more valuable constraint as you lose the energy in the quanta. So it should be cooling off faster now than it was before, which means that the pressure change is decreasing more. Right? So the pressure is going down faster, which means we're going to see more redshift. All right, so that explains expansion all to begin with, why there should be an accelerated expansion at the end in the phase we're in now.
Right.
And now all we have to explain is, where did this really big and really enormous inflationary period for the first fraction of a second come from? What do you think?
It's a good question.
Yes, it's a good question. So, right in the moment of the Big Bang, and we haven't really covered what caused the Big Bang yet here, so we're going to gloss over it shortly and we'll cover it more later, but a quanta from another perspective and our universe becomes a quanta from a zoomed out perspective, colliding with each other, okay? And all their internal components, the quanta that make them up, are compressed together from the collision, and then they rebound off each other.
Right.
Okay, so just from our internal perspective, all of our quanta got pushed together, and the geometry of space got pretty much closer like a black hole.
And this is right before this inflation that we're talking about.
Yes, right before the inflation.
Okay.
Everything got compressed, okay, and all the quanta of space are pushing together, or touched together. No superspace between them. So it's just like a black hole, except for a black hole, all the quanta settle down and just...
Right, they've lost their inelasticity.
They've lost their energy, right? So they're stable as a black hole. In this case, we force them all together, and they're all still charged with energy, and they're ready to go. So as soon as they rebound off, they're going to want to come apart and bounce off of each other.
Right.
Okay. So this condition, right when they're all pressed and just about to bounce off, since all the quanta are touching, there's no time in the universe, right?
Right.
Because you need to independently exist as a position to be able to freely resonate in order to experience time. Since all the pieces are together, we effectively have one point in space, right? Only one unique point. They're all together. If one
and it's
piece,
timeless.
It's timeless, exactly. So there's only space and no time. Now, as soon as the pieces separate just enough to get apart enough to resonate once, then a couple things happen. First, time now exists in the universe. Second is every separation introduces new unique points in space. Okay? The total number of quanta in the whole universe stayed the same, but the unique locations went from one to, as soon as the expansion goes, many, and then many more, and then it gets less and less because you've already started to separate most of them.
Right.
So that's what this expansion is, a change from one unique point in space to many unique points in space, and an introduction of time into the universe. Okay, so there's the inflationary period. It's incredibly fast, but in 11 dimensions it's actually required and quite simple.
That's
so
cool.
There's the mystery of dark energy.
All right, so 11 dimensions is pretty simple, intuitive. It's fun to listen to. And so now we've talked about gravity, dark matter, and dark energy.
Yeah.
They're all related and pretty simple to understand.
No longer mysterious, huh?
No, cool, but no longer mysterious.
Good.
So.
All right, so what do you say we get out of this heat now and
Sounds great.
cool off a little bit?